All right, so work, energy, and power. All right, first off, when we define work and energy, they really define each other. So work is the transfer of energy. And so that could be the transfer of it from one object to another. So you can think of that like um, when we have the wrecking ball swing back and then it swings and it hits a building, it's transferring that energy to the building. It can also, we can talk about the transforming of energy from different types. So for example, when this person is on the swing set, when they're really up high, we call that potential energy. And then as they're swinging, that's kinetic energy. Then they get high again, that goes back into potential energy. And so it's transforming back and forth. It's always the same object, but then it's going between potential and kinetic energy. So so it's either the transformation into different forms of energy, or it's that energy being transferred from one object to another. All right, so energy, though, is just the ability for an object to do work. So we have to talk about work to talk about energy, and energy to talk about work. Okay. Now, when is work done? We have kind of just normal everyday definitions of work, that work could be writing something, it could be thinking really hard, it could be lifting weights. But when we're talking about the physics definition for work, it is specifically the a force applied over a distance, and it only counts when the force is applied in the same direction as the object that's being moved. So what I mean by that is, in these examples, we've got a person who is applying a force to this box, and he pushes on the box and it moves forward in the same direction that his force was applied. So we would say that, yes, you're doing work in that case. Whereas with this girl who has her backpack on her back, she is moving and the object is moving with her, but she's not doing any more work on the backpack because it's already been lifted up. It's not getting any more energy, or there's no energy really changing form with the backpack. So in that case, we would say no. So those directions have to be the same direction for it to count. So when this woman is picking up her bag of groceries, because she's applying an upward force and the bag is actually moving up, we would say yes, that also counts. And then the last one, when she's then now has the bag in her hands and walks forward, that doesn't count because the direction of motion is not the same as the direction that she's actually applying the force. She's still holding the bag up, but she's not lifting it anymore. And so that does not count. So mathematically, when we talk about work, we're going to define it, we're going to define it as force times a distance, multiply. That also means a change in energy, because work is really defined as either transferring energy or energy changing forms. So for short, that's W for work is equal to F times D, force times distance. And then W for work again is equal to delta E. So that little triangle, that's the Greek letter delta. And it stands for change in. And so W equals delta E means work is equal to change in energy. And then last, if we say that A is equal to B and B is equal to C, then A has to be equal to C. So that means that our change in energy is equal to force times distance. Oh, one more thing on here. Please make sure that you get these SI units filled in. Force is newtons, distance is meters, work is in joules. And since work is... Okay, so here's our first example. You apply a force of 50 newtons to a box and move it 5 meters. How much work do you do on the box? So So we already know that work is equal to force times distance. So then what we need to do is fill in those values. So the force that we're applying is 50 newtons, and the distance that we're moving the object is 5 meters. So you just plug in 50 newtons times 5 meters, and that gives us 250 joules, just a J for short. All right, now in our second example, we have a bag of groceries that we're lifting. That bag of groceries has a mass of 8 kilograms. So we lift the bag 1.2 meters off the ground. How much work did you do? Okay, well, work is force times distance, but we have a problem. What is the force in this example? Well, the force that we're going to need to be able to lift this object is going to be the weight of the bag. So before we can actually calculate work, we're going to have to calculate the weight of the bag. So you will hopefully remember that the equation for weight is Fg is equal to mg. Force due to gravity is equal to mass times acceleration due to gravity. And we know that the acceleration due to gravity is 10 meters per second squared. So it's just Fg is equal to 8 kilograms times 10 meters per second squared, and that gives us 80 newtons. So please make sure that you fill in that information for this particular example. And then the next slide that you've got, you're going to fill in calculating work. So now that we have this extra piece of information that the force that we're applying to lift the groceries is 80 newtons, then we're going to multiply that times the distance, 1.2 meters, and we get 96 joules. Easy peasy, just some multiplication. All right, now that we've talked about how to calculate work, we're going to talk a little bit more about energy. We're going to focus on different types of energy. So these are all different forms of energy that you've probably learned about in previous years of science classes. Let's talk a little bit more about these two particular types. So you've got kinetic energy and potential energy. What I'd like for you to fill in is that kinetic energy is the energy an object has due to its motion. So kinetic energy is energy in motion. And potential energy, that is energy an object has due to its state or location. So its state could mean even chemically what state it has, like in a battery having the negative charge on one end and the positive charge on the other end, and that's why it allows electricity to flow. So it can be even like that, or it could be like in this example, you have the bow and arrow, and so the stretching of the bow, the state that the bow is in, because it's stretched out, that means it's got potential energy. If it's just sitting there and it's not stretched, then it wouldn't have any potential energy. So that's what I mean by the state or location. Now, I've given you some extra examples of kinetic energy and potential energy, and I want you to come up with 3 of your own. Okay, so please don't reuse any of the examples that I have. You can use those to inspire yourself, but nothing that I have listed here should be included. You can include things that are pictured here. So, these examples that you can see, and there's actually, I'm hiding an example, though that's stretched rubber band, which is already one of my examples. So you can use these that are shown here, but not one of the ones that I've actually listed as examples. But you need to have 3 kinetic energy and 3 potential energy examples. Okay, next, potential or kinetic. What I need you to do is to move these pictures so that they properly represent either potential energy or kinetic energy. So think about, is sound, is that going to be kinetic energy or potential energy? Is Is sound energy because of motion, or is it energy because of a position or state of being? Well, sound energy should be on the kinetic side because it is in motion. So think about these others, and then you can move on and see what the answers are. Okay, so on the potential side, we have chemical energy, nuclear energy, elastic energy, and gravitational energy. The elastic might be a little confusing to you based on the picture there, the tennis racket and the tennis ball. Like when the tennis ball is able to bounce, and so that's what the potential energy comes from. If it's actually flying through the air, then it would also have kinetic energy, so that's true. Things can have more than one type of energy at a time. And then like your battery here that's powering the light bulb, that would be potential energy, but the actual electricity that's flowing, because it's moving, current has to be moving, that's going to be kinetic energy. Okay, when it comes to power, power is the rate at which work is done. It's how fast work is done. And so one thing that I want you to, or something that I like to use to remember what power is I think of this little Power Rangers clock, and that reminds me that it has to do with time. So mathematically, power is calculated by work divided by time. And since we know that work is also calculated by force times displacement, or force times distance, then you can say that power is force times displacement divided by time. And we can change that and actually say, well, displacement divided by time is velocity, so power is equal to force times velocity. So those two equations that are in boxes, those are the important ones that you will want to know how to use. Also, the unit for power, which is joules per second, we call that watts. So energy is in joules and time is in seconds. And so if we do joules divided by seconds, we give that a new name, and it is watts. Okay, next we have a couple examples of calculating power. So you apply a force of 50 newtons to a box and move it 5 meters in a time period of 4 seconds. How much power do you use? Well, the first part is just calculating work, force times distance over time. So force times distance to get us work is just the 50 times 5, which we already did, and that was 250 joules. And then we divide that by 4 seconds, and we get 62.5 watts, or round it off to 63 watts, or even round it off to 60 watts if you really want to be specific with the sig figs that I gave you. Now in the next example, this is the grocery example. This time I changed the height, the distance that you're moving the bag, to 1 meter, and I added a time of 0.5 seconds. So you lift it in 0.5 seconds. How much power do you use? Okay, first off, got to figure out that work. We know that the we know that the force in this one, I went ahead and gave you the force is 80 newtons, and then the distance that we're lifting is 1 meter. It was 1.2 earlier, but now I've changed it to 1. And the time is 0.5 seconds. So we can go ahead and do this piece first, the distance over time. And what I'm doing there is I'm actually doing the equation that was power is equal to force times velocity. So that's 80 newtons times 2 meters per second. 1 divided by 0.5 gives us 2 meters per second. And so that would give me 160 watts. So it doesn't matter if you do force times distance first, or if you do distance divided by time first, you're still going to be able to get power. Okay, this is just a little summary of the stuff that we've covered today, and that is, I'm not going to read the whole thing to you, but it's a nice diagram to explain the relationship between work, power, and energy. And so you can take a look at how those things are all related to each other.